So what drives the plates? Now we've learned that the plates are moving. They are constantly in motion. They're subducting, they're diverging, they're converging, they're transforming. They're doing all kinds of things, but what actually causes them to move? Well, that's what we're going to talk about today. All right. Well, one of the key players in understanding this is something called density. Hey, we know what density is. What's density? Density is the mass of something divided by its volume. Now, there's a big misconception amongst students, I think, and I think they misunderstand the concept of density. I think when you think of something sinking or floating, what do you think of? You think of something heavy or light. And that is, I think, not true. It's not true, it's not true, it's not true. What causes something to float is density. I'll bet you've ever looked outside at an ocean or a big lake, and you've noticed a boat on there. So let's say we've got a boat on the ocean. All right, there's the boat. Could you lift up that boat? I bet not. It's heavy, isn't it? Does it sink? No. You see, density has to do with sinking and floating. You see, the density of water, by the way, just for fun, water has a density of 1.0 grams per milliliter. The boat has a density that is less than 1, even though it has a greater mass. Okay, so it has to do with its density. Things that float versus things that sink. The rule is that the more dense thing will sink in the less dense substance. So if I were to take a rock, okay, most rocks, not all rocks, but I take a rock and throw it in the water, it will sink to the bottom of the ocean. Why? Because it is more dense than water. So it has to do with floating and sinking. Now, why am I talking about floating and sinking when it talks about plate tectonics? Ha! It's because things have different densities. Why don't you copy down this table, an important table here. There are continental crust, oceanic crust, mantle, outer core, inner core. These are the things that make up the Earth. All right? The important thing I want you to understand, actually, is really to look at the two extreme edges right here. Here we have the continental crust, okay? And in the continental crust, we can determine that the density of continents is 2.8. Primarily because it's made of granite. Granite has a density of around 2.8. By the way, that will sink in water, but it's actually the smallest of all the numbers here. Because if you go to the oceanic crust, right? Ocean crust, 3.3. So who sinks? Ah, the ocean sinks below the continents because he's 3.3. More dense substances, remember, sink more. If you go to the mantle, his density is 12. Oh, my word, have mercy. Woo! That's a lot. Compared to 3, and the outer core and the inner core are the same. So the more dense things sink to the bottom. But since these, the less dense things, rise to the top. So the crust, the two varieties of crust, oceanic and continental, they rise. Another thing I want to say about this, and you want to write this down too, interesting thing you notice here is the temperature. Look at the temperature here. The temperature of continental crust, 20 to 600 Celsius. Oceanic, 20 to 1300 Celsius. 100 to 3000. 300 to 6500. 7,000 degrees Celsius. So what's the general rule? The deeper you go, the warmer it is. Why don't you write that down? The deeper you go, the warmer it is. If you've ever been in a mine, the deeper the mine, the warmer it is. There's mines in South Africa where they mine a couple of miles down, and they're mining for diamonds. And the people there have to wear protective clothing because the heat is so much. Even if it's freezing cold on the surface, it is absolutely very, very hot inside. You got to drink a lot of water inside, of course. Okay, let's take a look at the Earth. Okay, sketch this or print it. You, of course, realize the outside's called the crust. Okay, that's that little, very thin part. And then we have the mantle. Okay, and then we have the outer core and we have the inner core. What they're made of, well, we'll learn about that. Actually, that was in that slide before, wasn't it? All right, what are they made of here? Okay, granite, basalt, silicate, liquid iron, and solid iron, and nickel, actually. Okay, so why don't you, actually, what would be kind of nice to do is on your chart, you could say right here the mantle, right here for mantle, and you might just say what makes it up and what its temperature is. So actually this chart, it'd be kind of cool to take this chart and put it onto this picture. There you go. So you could say iron and nickel right here, right? An iron and nickel, and this is iron and nickel. We're running out of space here, but you get the idea. Okay. Now, here is the big question of this particular section. What causes the plates to move? The primary thing that causes plates to move is something called thermal convection. Everybody say thermal convection. Thermal convection. Thermal means heat. So it's convection. Convection is something that is something that's indicative of how heat moves. If I've got a hot plate, which we'll show you in just a minute, and I put a beaker on it, okay, so there's a hot source. This is hot, woo, hot, hot, hot. It's very hot. And I add the liquids, solids will do this too. the energy will rise, but then as it rises, it cools, and so it will fall. So it makes these convection currents. Look at this picture right here, and you can see those convection currents. And then those convection currents, if you've got something floating, if we somehow had something here floating on top, it would cause it to separate. Okay, a solid sort of shell, hence a crust. Okay, here's another picture of it. Next, let's go ahead and watch that video clip that we've seen before, actually. All right, I want to talk about the concept of a convection cell. Now, if you look here, I got some beans in a beaker of water. And if you see the beans in the beaker of water, they're kind of going up and down. They're following this pattern that we talk about going up and then down, up and then down. That's the same pattern that we see inside of the sun. We also see it in thunderstorms. They go up and down because you have a heat source at the bottom, this hot plate, and as the little beans go up and down, they follow a pattern, a circular pattern if you watch them, and that explains the convection zone of the sun, how it works, because you've got the internal heat source, the core of the sun, and as the energy rises, it takes the gases, in this case the beans, I guess, and causes them to rise and fall. So that's how it works. So hopefully that helps you understand thermal convection. Isn't that cool? All right. Actually, also to do this, I want to also do another video clip. Where'd it go? Well, we're also then going to do a thermal convection animation, so we can see what that looks like. So let's see what that looks like. Okay, now let's just kind of, here's the content. There's quite a few things I want to talk about here today. I don't know, there's like 10 bullets, so this will be a longish podcast. Sorry, a lot to learn. Okay, layers of the Earth we've already talked about. So, I think we've already hit this topic, so let's just skip that. All right, and then here is something I do want you to also note here. We've already talked about this too. Man, we're amazing. Okay, we're moving on. But this something is new. How do we know that the Earth is what it is on the inside? How in the world did we figure out? Has anybody dug a hole to the core? And said there was an old movie, it was really bad science, called The Core. No one's ever been to the core. How do we know it's inside the Earth? Well, the answer is it's because of earthquakes. Okay, we haven't had a chapter on earthquakes, but we will soon. But if I have an earthquake over here, it produces two kinds of waves, P waves and S waves. Okay, we'll learn all about earthquake waves later, but it's just important to understand P waves and S waves. Well, it turns out S waves can't go through liquid. Nope. Liquid? Nope. Can't. Whoa, hello, what do? Can't make it through a liquid. Hello, my pen just attacked myself. Okay, so when the S waves, so there's actually more than two kinds of waves, but two kinds of waves that we can study. When the S wave, so an S wave comes here, boom, and hits the liquid, it stops. Can't go through there because you see there's a liquid there. So that's how we know where the inner core is. Okay. Now the P wave is an interesting thing. It can go through a liquid. So when it hits this liquid, it bends. It bends because of something called refraction. Oh, we remember that. Refraction is when you bend something when it goes through a more dense substance, or a different density, not actually more, it could be less, and it gets bent. And so we can calculate this angle right here, I'm repeating myself, the angle right here, and you get that angle, and then it gets another angle, and so we have a seismograph station over here on this portion of the world, and we can actually figure out the size of the Earth based on these P and S waves. So it's really, really fascinating. Right. Another thing that's going to help us understand what causes the plates to move is Newton's law of gravity. We've learned about that. Remember, this is F equals a G times a M1 M2 over R squared. Remember, G was 6.67 times 10 to the minus 11th. Remember that number? We did all the math for that in our astronomy unit, or we will if we're doing this first semester. So it's a big, big number, isn't it? It's just this big math equation, but that tells you that all things are attracted to each other. But the more massive to the less massive, or the less massive to the more massive. Basically, the idea is that things are going to move towards the center of the Earth as much as possible. So gravity plays a role in all this. The thing's kind of basically going in a downward direction. Okay?